mind's eye of the modern physicist, of the lowest energy state of the simplest atom. The electron occupies a cloud instead of an orbit, but its most probable radius, and also its energy, is equal exactly to the values given by the Bohr model that came before it. But wherever in the universe it happens to be, the hydrogen atom is not always found in its lowest energy state. Like the Bohr model, the quantum atom has a different energy for each integer value of the number n. That energy results from the shape of the electron cloud. For n equals 1, called the ground state, the shape is a symmetric cloud, the same in all directions. For n equals 2, there's a state with a double spherical cloud, one inside the other. But for the same value of n, and therefore the same energy, there's also a state with a donut-shaped cloud that almost suggests an orbit. This state has another integer, L equals 1, associated with it. N and L are called quantum numbers. And because the cloud isn't really an orbit, it's called an orbital. For example, there's another orbital with the same quantum numbers, n equals 2 and L equals 1. The same n means the same energy, and the same L means the same angular momentum. In classical mechanics, any orbit has a definite angular momentum. In quantum mechanics, certain orbitals have positive angular momenta, starting with the smallest allowed value, a little more than h bar. But the vertical component is exactly equal to h bar. That's for an orbital with L equals 1. However, though the vertical component is determined exactly, the actual direction of the angular momentum is quite uncertain. It can lie anywhere on the surface of this cone, and instead of being in orbit, the electron is in a donut-shaped orbital. So, for n equals 2 and L equals 1, the electron orbital is a donut around a vertical axis. The angular momentum is anywhere on a cone around the same axis, and its component along the axis is exactly h bar. But that's not the only possibility. With the same n and L quantum numbers, the angular momentum could be horizontal. In fact, it could point anywhere in the horizontal plane. Then its vertical component is exactly 0, and its orbital isn't a donut, but two clouds, one up and one down along the axis. And finally, its angular momentum could tilt downward, producing a mirror image of the orbital of the up state. So with the same energy and angular momentum, n equals 2 and L equals 1, there are three distinct quantum states. They could be called up, middle, and down. But instead, a new quantum number, m, is given the values +1, 0, and -1. And of course, the story doesn't end there. For n equals 3, there's a whole new set of orbitals. Concentric spheres for L equals 0. Concentric donuts for L equals 1. And also double clouds up and down. These correspond again to m equals 1, 0, or -1. But now, L can also equal 2. These states come in a single donut version, a new variety with one donut up and another down, and another featuring a donut and two clouds. These correspond to m equals +2, +1, 0, -1, and -2. So here's the basic architecture of all the quantum states of the hydrogen atom. N can be any positive integer, starting with 1. And for each n, integer values of L are allowed from 0 up to n-1. Finally, for each L, M can go from plus L to minus L. This same basic structure will turn out to describe not only all the possible states of the hydrogen atom, it will also serve to explain the entire periodic table of all the chemical elements. The Greeks thought there were 4 basic elements: earth, air, water, and fire. As time passed, more and more elements were discovered, and by the 20th century, they numbered almost 100. Yet for all their diversity, all the elements owe their existence to a trinity of subatomic particles: neutrons, protons, and electrons. Like hydrogen, each element has many energy states. But for chemical properties, the most important is the lowest, the ground state. And the ground states of all elements follow the pattern of the excited states in the hydrogen atom. That state of affairs comes about because of 2 very peculiar quantum mechanical properties of the electron. One is the fact that the electron has spin. Not that it literally spins like a little Newtonian sphere, but it does have an intrinsic angular momentum, just as if it did. Its magnitude is a bit less than h bar, and its vertical component is exactly 1/2 h bar. And just like the angular momentum of an orbital, the spin angular momentum can be found with equal probability in any direction along a cone. That cone and its vertical projection can point up, or it can point down. Those are the only possibilities. Nothing in between is allowed. The second quirk also has to do with the electron's quantum mechanical inner nature. No 2 electrons can ever have exactly the same quantum state. In other words, the probability of 2 electrons occupying the same state is exactly 0. That means no 2 electrons can ever have exactly the same quantum numbers in the same atom. But spin is itself a quantum number. So, if one electron has spin down and the other spin up, they can share the same orbital state. These, then, are the fundamental rules that govern the chemical elements, the stuff of life and everything else in the sea, on land, and in the heavens. The rules are these. Each atom can be thought of as an ion, the nucleus plus the inner electrons, with one final outer electron needed to complete it. That electron goes into the next, lowest energy available orbital and spin state. For example, 2 electrons are permitted in the n=1, L=0 orbital. The first one completes a hydrogen atom, and the second, with opposite spin, completes the atom of helium. This completes an energy level, making helium chemically inert. The n=2 shell of orbitals has room for 8 electrons. The first, with L=0, makes a lithium atom. The next, with opposite spin, makes beryllium. Now room must be made in the periodic table for atoms with orbital angular momentum, quantum number L=1. The first is boron, followed by carbon. These states have slightly different energies, even for the same n, and as each element is formed, it chooses the lowest energy state available. Following that rule, the shell fills up with nitrogen, oxygen, fluorine, and finally, the chemically inert noble gas called neon. According to the basic rules of atomic architecture, the n=3 shell will have room for 18 elements, starting with sodium, then magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and the noble gas argon. But then a funny thing happens. Because of forces between electrons, the next lowest energy orbitals are at the ones with L equal